So when we look at that average atomic mass, we're usually not going to get a whole number because almost every element that exists in the universe has a couple different versions of itself that have different weights. So remember that average atomic mass that we see on the periodic table is going to be that average of all the atoms that exist. The other thing that we can sometimes get, and this isn't always provided for us on the periodic table, but it does give a good amount of information, is what's called the mass number. So the mass number is where we have the total weight of that individual atom. So the example that I've given is uranium-232. So uranium-232 is one of the isotopes or one of the versions of uranium that can exist. And this 232 that's given tells you how much that particular atom weighs in atomic mass units. So uranium U-232, it weighs 232 atomic mass units. So that's its mass number. Now you can figure out how many protons and neutrons are in this uranium-232 by looking at the periodic table. So if you look at the periodic table, you have uranium, its average atomic mass is 238 point, what is it? Let me see here, 0.029. And it has an atomic number or number of protons equal to 92. So I know how many protons are in there. And because the mass number is equal to protons plus neutrons, so it's the protons and the neutrons together. If I know the mass number is 232 and I know that I have 92 protons, I know how many neutrons I then have. The comparison with that is if you look at something like U-235, okay? It has, again, 92 protons because all uraniums have to have 92 protons. But in the case of U-235, which is a little bit heavier in comparison to U-232, this one has 143 neutrons, making it an isotope, which we're going to learn about a little later, which an isotope is basically another version of an atom. So sometimes you're not going to be given a mass number. You're not going to get that whole nice number that's sometimes given to you, like U-232 or carbon-14. If you're not given that number, what that mass number is, what you can do is look on the periodic table. So let's say we're looking at oxygen, okay? If you look on the periodic table, oxygen's average atomic mass is 15.9994, okay? And it has 8 protons. So what I can do is look at that average atomic mass and I want to round that to the nearest whole number, which is going to be 16. So generally, if I don't give you that mass number with the symbol of the element, what you want to do is just look at that average atomic mass and round it up to a whole number. So the big question that we get a lot is that how is it that atoms can differ? Well, they can differ by 2 of the subatomic particles that exist within an atom. Protons can never, ever, 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 ever differ for an atom. So if we're looking at lithium, all the lithiums that exist in the entire universe all consist of 3 protons. If they don't have 3 protons, then it's not lithium, it's something else, it's another element. However, the other 2 subatomic particles can differ. If we have different number of neutrons, let's say we're looking at carbon-12 versus carbon-14. Carbon-12 has 6 neutrons, whereas carbon-14 has 8 neutrons. So that weight difference can be utilized in different ways throughout chemistry. So one of the ways that we use isotopes with carbon-12 is we try to figure out how old fossil remains are based on how much of this carbon-14 we can find, okay? Another way we can use isotopes that's actually really helpful in terms of nuclear production is that some of the isotopes we get of things like uranium and plutonium are indeed radioactive, and they're radioactive with only that one version of that isotope. Okay, so we can use some of those sometimes for energy harnessing because they're not very stable. The other thing that we can differ with atoms and change them a little bit is by changing the number of electrons they have. So remember, in a neutral atom, the protons are going to be equal to, oops, didn't want to open that. Back to Notability. 1 second. Okay, so let's say we're looking at protons and electrons. Protons and electrons should be equal to each other, okay? But in an ion, they are not equal. Electrons can be really easily gained or lost in an atom because if you remember the way an atom looks, we have the nucleus in the center, and then we have kind of these regions where the electrons live around them. Those electrons that are on the outside of that can get pulled off right away. Something else can steal them, or the atom can take some more electrons from someone else. So the number of electrons changes all the time for atoms. When we have the protons and electrons not being equal, that is what we call an ion. So it's going to make the overall atom either positively charged or negatively charged. And we're going to see that in a second. So how do we know if we have subatomic particles that have changed within that atom? So if you're looking at something like ions, the way that you know that you have an ion is that you're going to have a plus or a minus sign with a number by it. So let's say we see something like F minus 1 or Na plus 1, okay? These pluses and minuses with the number beside it tell us about the electrons that happened. If we have positively charged ions, okay, let's say something like sodium plus 1, okay, that means that electrons have been lost from that atom, okay? So that sodium has lost an electron. And the reason why it gets a plus charge is because sodium, if we look at the periodic table, sodium has 11 protons, and it usually has 11 electrons to give it a neutral charge. However, if it's lost an electron, that means it has 10 electrons. And if you remember, protons are positive, electrons are negative. If you have 11 positives, 10 negatives, that's an overall charge of plus 1. So that's why if we lose electrons, it actually becomes positive. And then if we have something like fluorine minus 1, fluorine normally has, 9 protons. But if it has a minus 1 charge, that means now it has 10 electrons, giving an overall charge equal to negative 1. Okay, so again, it's kind of that opposite thing with the ions. With isotopes, the way that you can know that you're looking at an isotope or that you're looking at kind of a special version, a different number of neutrons for that particular atom, is they're going to give you this mass number directly following the atomic symbol. So U235 versus U232, that could also be versus U238. There's a lot of different versions of atoms. Some atoms have probably 20 different types of them with different mass numbers. Some of them only have one type. It really just depends on the individual atoms and what we've discovered about them in science. So what we're ready to do right now is we're going to do some practice. So what I want you to do is I want you to look at this chart. And I want you to copy this down on a piece of paper. So this is kind of going to be an example, a practice session for us to look at how you calculate subatomic particles. And I'm going to go through and do the first one with you, which is oxygen. So oxygen has a symbol of O. So if I look at the periodic table, oxygen's symbol is O. And its atomic number is 8. Now the atomic mass, I'm not given it over here. Okay, I'm not given like any kind of a dash with a number like you might see here down with carbon-14. So if I'm not given that atomic mass, I want to look at the average atomic mass and round it. So the average atomic mass is 15.999. So I'm going to round that up and say that the atomic mass is 16. Okay. Now I know that if the atomic number is 8, then that must mean there are 8 protons. And if I take the atomic mass, which is 16, subtract the number of protons, that gives me the number of neutrons, which is 8. And then electrons is going to be the same as the protons because we have a neutral atom here.